So here we are. So this is a rather interesting section, which I think is suitable for what we would call an advanced topic, because really it tests your math, but also how you look at physics and try to frame the math problem. So very similar in nature, where a concept of physics or mechanics is taken, but really the test is mathematics, right? It's really where you have variations. So up until now, we've studied, where velocity is constant, and then it's just displacement, or rate of change of displacement as velocity, but that velocity is constant, and then therefore acceleration is zero. Or you have some cases where, velocity is changing, rate of change of velocity with time, and then you have an acceleration, and then you have constant acceleration. But now we'll start with this fundamental idea: what happens when there is not a constant either in acceleration or velocity, and obviously by inference in displacement. We'll start with let's say our basic idea, right? Our basic idea, we know, is that if x, so we'll do this, we'll write this as our direction, right? And x is our displacement. And we know that the derivative of x with respect to time gives us velocity v. This much we know. And acceleration is the derivative of velocity with respect to time, which then means it is the second derivative of displacement with respect to time. So pretty much these are things we've dealt with. We know how to make it work, but now we want to redo this. And as you can see here, I can write acceleration obviously as a function of x or t. But now we want to redo this and say, in very simple terms, given an x as a function of t, right, I can now state the following relationships to be true. If I integrate acceleration as a function of time, I can write v as a function of time. And if I integrate velocity as a function of time, I can write displacement as a function of time. Still in the fundamentals of calculus and physics, right? We are here so far, we are good. Now what happens when we start creating these variations? So first one is, let's say, acceleration varying with the time. So that is very simple. It's as I stated here. So you are given a problem that says, here's an acceleration, and here is a function, acceleration as a function of time. All you do is you go in and say, okay, first I'm going to attempt to integrate it, and I will say velocity is equal to the first integral of the function of time. I get a value, but I must add a constant. Now this is the part where you can get caught. Typically a question will always have a boundary condition, which should allow you to then go in there and say, hey, what that constant is. And sometimes it can get tricky. Now I can also redo this and say x is equal to, now look at the boundary condition altering, right? Because it's the integral of f of t and the integral of c, right, with t, so that becomes c times t and another constant d. So be very mindful of how this is. So yes, you integrate that, you get a constant, but that constant then gets the t, because when you differentiate, remember, that becomes 0, that becomes c, and this just becomes the integral of f of t. Differentiate it further, this becomes f of t, and that becomes 0, and you get acceleration. So be mindful of how the problem is set up, and that's really what I want to get to. I don't want to be doing integration problems here, because you probably have learned it, and be very careful about how integration problems get set up. You must know that if you're integrating, or if you're differentiating dv, as is the case here, if you attempt to differentiate dv, or if you're trying to integrate dv, you need a v dv to be integrated, right? You can't do an x dv, right? So be mindful of how you set up the integration problem, and that's key. But I will now stretch this a little bit and say, what if I position, right, or what if I now state this acceleration as being dependent on velocity, right? If I state the problem that way, let's say I make acceleration a function of velocity. So this is a classic case where if I attempt to say, how would I look at its derivative? Because I know that acceleration is just dv by dt. So I have to be very careful of how I manage this, because if I now try to do an integral, it's not just integrate and get v, but how am I going to integrate this? Because I don't have velocity as a function of time. So I wouldn't be able to necessarily perform both integrations with respect to time. So I will have to play with this here, and then kind of rewrite this to something to the tune of, and I will say the integral will be some function here, which could be the reciprocal of this, which is really another function, dv is equal to the integral of dt. That should allow me to come up with an equation in v equal to time plus a constant. Apply a boundary condition to that equation, get the constant done, and if required, rewrite this function as as velocity in terms of time. So you might have to solve the function here. Again, several examples. I won't go to the math of it. You should know the integration pretty thoroughly, but be careful of how you get these problems when you get, if you get a slightly complicated function here, then the integration is not as simple. You might have to do some factorization and things like that. So that's addressing acceleration as a function of velocity. Now, I'll take a third case. Let me remove all the easy stuff that you know out of here, right? Let me take a third case, and for the third case, I want to use, let's say I use an orange color, and say, I have a third case where I say, I give you acceleration, but as a function of displacement. And this is where it gets even trickier sometimes, because now I have an interesting case, because I have dv by dt, and even if I attempted to manipulate this and move them around, I will never be able to get there. So I have to come up with a means of addressing it. So how do I address this? I think the best way to think about it is to say, if I have dv by dt, I can write it as dv by dx times dx by dt. This is basic calculus, right? Or rather, you must know this in calculus, which then would mean dx by dt is nothing but velocity. So it's velocity times dv by dx. So I can write acceleration, which is basically that, as v dv dx. But I can also now extend this idea a little more, right? And if you really thought about this, if acceleration is given to me as a function of f of x, so if acceleration is provided as a function of f of x, now I'm substituting the two, I'm writing f of x, right, as equal to v dv dx. The problem we were working on is acceleration as a function of x. Now think about it this way. Now I can write the integral pretty easily, right, by moving them around. I can say v dv is equal to f of x dx. and apply the integral, right? And then v dv is nothing but v squared by 2 is equal to the integral of acceleration as a function of x times dx. I hope you're with me on this. So this is another way of writing it, but the whole idea is where do we apply them? So here, when you're given acceleration as a function of time, very straightforward. When you're given acceleration as a function of velocity, make sure you do the adjustment here for the velocity function in order to get the dt. But supposing suddenly the problem begins to ask you about finding a distance and expression of distance, then you again have to go back to making velocity as a function of distance where you come here. So if I'm just going straight to the equation, I can go here, take that function by dx, and I know it's, whatever is the acceleration function, not the velocity function. And if I have a velocity function, it's as easy as saying, if I took that out, so just to make it easy, and if you remember, v dv by dx, and is also equal to d by dx of, say, v squared by 2. Right? So if given a function in terms of displacement, that would be my derivative form. So I could just bring that function here, and this is what I would get. Vx by 2 would just be v, right? So I could write my function this way. So something to bear in mind when you see different options. So the v dv is probably the most common that you'll see. Much less applying this, but more obtaining this format. So if I was told that the acceleration is a function of velocity or is a function of displacement, then that's how it's structured. But what if I was given acceleration as a function of, well, this is the third, probably more interesting part. If I gave you acceleration as a function of velocity, then you have two approaches. Your approach one, right, here is very straightforward. Right? And you use this when you want to get a time value in the problem. But what if the problem is asking you for a displacement value? Then you write that same function, right? You've got this, you can write it here, right? And you would basically you would write this v dv here and solve it from this format, and you would rewrite basically v dv dx is equal to f of v. Apply the same logic here, v by f of v dv equal to dx. Work the integration out, and you can solve an expression for x. So remember, this is valid when you get one of these a is equal to. So whilst this appears very simple because we're staying in the realm of time, you can go there, but you have to come back here the moment the problem asks you for displacement related things. So how much, what is the distance traveled for velocity to increase from x to b, x to y, or a to b, if acceleration is a function of velocity? Well, then you apply this. If acceleration is given as a function of velocity, then you go back into this equation, right? You move this here, perform the integration to get it with respect to x, and then you have a factor. You have boundary conditions, assuming initial displacement velocity is 0. You can get a constant of integration, and then you apply your two values of velocity to get x values, and then look at the difference, and you get the displacement. So that's the approach. So this is if you get the concept in physics of what is happening, and you know the foundational integration and differentiation, it works. But where that concept becomes an application that can get tricked into a problem is when you are presented with the problem either as look at that. I've given you acceleration as a function of time, acceleration as a function of velocity, acceleration as a function of displacement, and my treatment in the case of velocity can be in two directions. Displacement clearly always comes here, and time is very straightforward. So how I set up the problem, and that will give me the answer, right? And sometimes, yes, you do have two ways of doing it. You can have a velocity function given to you, and you can do the derivative. You can find right velocity in terms of time, get the boundary conditions. Once you have velocity in terms of time, you can then integrate that function to get displacement. It might be longer, right? Think about it this way, right? I've got this. I've now got this in terms, and I can write now a v in, I can write, go back to green. What happens here, I can write v as now a function of time. Then I can apply my integration here to get x is equal to the integral of that plus a constant, again boundary conditions, and I can solve for x. So I can do that, or I can come here right away and attempt to do it. So there are two approaches into some of these problems. One of them maybe you read the entire problem, because sometimes they ask you for the time. They say, tell me velocity in terms of time, and then might ask you what is the displacement or distance covered in X amount of time. It's a lot easier to do this, because if you try to do this, you'd only have distance in terms of velocity, then you would have to bring in the previous equation. So read the two parts of the question so you can determine which direction they want you to take with this. So that's the key essence here when it comes to understanding the variation of acceleration. But I want to now stretch this concept a little further. I hope you're clear with all of these. So I'll take all of these out, right? And I'll just keep that one section here. Actually, I keep these two, right? Keep these two here. And I want to get to the concept of taking, if acceleration can vary, right? And I've talked about acceleration varying with time. I can also write an acceleration that varies with velocity, right? I can write acceleration as a function of, I can write velocity as a function of displacement. But what happens when acceleration changes? We know that force is mass times acceleration, but that really means force is changing. That means I have a variable force. And they like to throw problems in typically horizontal motion with variable force. We will also talk a little bit about variations on the vertical dimension, but I think there's only a special case in oscillations and that we'll look at. We're not going to look at it overall, but you can fundamentally think of it this way, right? Where did we see variable force in the past? In the past, we've seen variable force when an object is falling, right? We just thought that it was mg, right? But what happens in real life is if you're falling from a great height, you're going to meet with air resistance. So there's mg, but there's also air resistance that's working against you. And as you approach the surface of the earth, the air resistance increases, and it's not a fixed air resistance. So air resistance is increasing with time. So the R here is a variable resistance. RA is a variable resistance. Your net force therefore is also a variable. It's also a function, either with respect, and it's usually with respect to displacement. It's as far as depending on, so net force becomes a function of displacement. If you can see here, if net force is a function of displacement, it's similar to coming up to acceleration being a function of displacement. How do these problems get treated? So when you treat these problems, again, you equate the two sides of what's going on. You have a function, an acceleration function, which is basically m times a function, either given to you as m times f of x, and then you equate that with the force, which is basically ma, that is given to you, right? Sometimes it's m times v, but then all you do now, this is where the math becomes similar, because once m goes away, everything else is like your previous problem. You just don't integrate as is. You go back to say this is v dv dx. You move the x here. You do the integral of f of x dx, and v dv, the integral of v dv is v squared by 2. So that's how a typical problem gets set up here. So understand the force. The only difference also that you need to keep in mind is because most of these problems are happening in one dimension, you might as well treat them with directions. So you might end up in a case where, if I have motion in this direction, some velocity, the application of the force is usually here, right? I might have this written as a function of displacement in that direction. So you have to be careful to when you net them out and say, hey, I have mass times, so the force is given to me, so it's some ma, right? That is usually negative of this function of, and you're given velocity as a function of time. So again, you would write mass. This is the integral of, derivative. It's d by dt of v of x, which doesn't make sense. So that would be negative mv dv by dx. So you'd set your problem up like that, right? And then if you have a force function in x, it's easy. If it's a force function in t, no brainer, because you have dt and it's an easy one. If it's a force function in x, you'd come here, right? So if force is given as a function of t, you just bring dt here. But still it wouldn't balance because you have an x. So that would again create problems. So you have to ensure you rewrite your functions correctly to get this. But hopefully this gives you an idea. And hopefully I'll give you a segue to start thinking about another question I asked when we did elastic springs and elastic strings and springs. I did ask a question of, supposing you had a elastic string here with a mass, and you were going to pull it down. So this is L and this is X, right? And you pulled it down and you let go. You'd see it moving back, but we know tension is equal to lambda x by L, which means as x, and that's force, right? So if that's the force, so this object is undergoing directional motion of some form, it's accelerating. So negative mass times its acceleration in that direction will be equal to, let's say, that force. If I write that force as delta x times delta by L x, right? Because as the x reduces, tension changes. So tension is moving. So they're all in opposite directions. And if you think about it, and actually I have to multiply that with mass, right? But yeah, let's just look at it this way, just for the sake of it. I can just write this function as, this is nothing but the second derivative d square of x by dt, and I can write this as negative. Think about it this way: if this is a constant, this is a constant, mass is constant, x, right? It's almost like writing the function d square x by dt square plus x equal to 0. So I can write some of these interesting equations here, but this is a classic case in an elastic string or a spring where you can have variable force. So I just wanted to introduce that, and that I think will be a good segue to the final area that we will explore, which is oscillation, simple harmonic, whether it's vertical or horizontal. But for the purposes of the curriculum, they've broken down into kinetics and dynamics. They talk about variable acceleration with time, velocity, and displacement in the kinetics section as 3 separate sections, and the variable force problem is addressed in dynamics, in the beginning dynamics. But I thought they kind of The logic is the same. The kind of mathematics is the same. How you place the problem slightly varies, because in the force equation, you will specifically ensure that your directions are captured, right? Because most of the time it's horizontal direction with the force that is provided to you being working against motion. Otherwise, you wouldn't have to worry about it at all. It'll just be a standard acceleration with displacement, or it'll be quite standard as this. The very fact that this idea is introduced is because force works against you, so you would kind of rewrite your functions this way. So that's the only variance that you need to capture conceptually. So I will leave you with this for this topic. I'm not going to go there. There's an infinite ways this problem can be structured. Like I've shown you, they can give you functions in different forms. Usually they don't bother you with overly complicated functions, but it is common to say, and you can almost always look at the problem and see the extent of lines that they've spaced things they've given you after the question for the working. And if you see too much of it, then you clearly know you are dealing with a variable acceleration or variable velocity, or velocity as a function of displacement type problem. So variable acceleration or velocity as a function of displacement, both of them require a fair amount of integration. So keep that in mind. Many times you do need to show some steps of integration. You can't just bypass it using a calculator. So also keep that in mind. Ensure you get your differential variables accurately captured on equal side on either side of the equation, so that the integration can be meaningful, right? And some integrations require factorization. That's pretty much the math and the physics that's required on this. Yeah, not too long. I really think it's the understanding of this concept that makes that is valuable, and where you frame the problem and how you do the v dx or just dv by dt, right? So think about that and practice more problems. This is more problems you practice, the more you get used to it, and some of them do them in both ways so that you can see which one is faster, right? I will see you in the next advanced topic, which is oscillations and harmonic motions, which I think will be the last for the A-level curriculum. Right. Thank you.